This is Materials Project number 4, made by Alex, Cole, and Stewart. The iron bar starts at 1 meters in length between two rigid walls at 20 degrees Celsius. The bar then heats up to 100 degrees, forcing the bar to elongate. How we found this was by subtracting the initial temperature and the final temperature and multiplying it with alpha and the initial length, and then adding the initial length to get the final length, which came out to 1.00096 meters. The stress on the iron bar when it goes from 20 degrees Celsius to 100 degrees Celsius is shown by the equation shown below of the negative elastic modulus times alpha times the difference between the final minus the initial. The elastic modulus is 210 times 10 to the 9th pascals. Alpha is 12 times 10 to the negative 6. And the difference between the temperatures is 80 degrees Celsius. Putting that all together, it comes out to 2.016 times 10 to the 8 pascals. The aluminum bar for this experiment goes through the same temperature change from 20 degrees Celsius to 100 degrees Celsius. Using the same formula as we used for the iron bar of the final minus the initial divided by the initial times alpha times the difference of the temperatures, and the alpha for aluminum is 23 times 10 to the negative 6. Putting that all together, we get 1.00184 meters. The stress for the aluminum bar from 20 degrees Celsius to 100 degrees Celsius is shown by the same formula as the iron bar. The elastic modulus for aluminum is 70 times 10 to the 9th pascals, and the alpha for aluminum is 23 times 10 to the negative 6. Multiplying them all together with the difference between the temperatures, it comes out to 1.288 times 10 to the 8th pascals.
All right, so let's expand this equation and then just solve for our deformation total. And let's just do this for aluminum at first. So our thermal expansion coefficient times our temperature plus our stress over our Young's mod and let's add some numbers to this. So 35 times 10 to the negative 6 times 10 to the negative 2 plus negative 1.815 times 10 to the 8th, since the stress is a compressive stress. And then that's over 70 times 10 to the 9. And we just sum up these numbers. Quick math, you get negative 0.0029. and that's the deformation total of aluminum. But if you think about this, this means that the aluminum has shrunk and the steel has expanded and pushed on the aluminum to shrink it, because it wouldn't just shrink on its own due to the temperature increase. So the steel must have expanded out by this 0.29 millimeters for the aluminum to shrink by that amount. So the length of our beams will be 1 plus or minus this deformation, with aluminum being the minus and steel being the plus. And that would give us our final answers of length of aluminum to be 0.9997 meters. And our length of iron to be 1.0003. Very small deformations, but it's still a deformation nonetheless. For the second part of this project, we were tasked with simulating the diffusion of atoms from a high concentration to a low concentration with differing temperature and amount. For our control, we had 200 atoms at 300 degrees Kelvin. For our second test, we had 100 atoms at 300 degrees Kelvin. And for our third test, we had 200 atoms at 50 degrees Kelvin. If we compare our control to our 100 atoms test, we can see that the 100 atoms test is much lower after 30 picoseconds. And this makes sense, as the flux is directly proportional with the concentration of atoms over a distance, and having a lower amount of atoms would in itself mean that there is a lower concentration of atoms, given it's the same amount of space. If we then compare our control to our 50 degrees Kelvin test, you can also see that the 50 degrees Kelvin is much lower after 30 picoseconds as well. And this makes sense, as the temperature is directly proportional with the diffusion coefficient, which in itself is directly proportional with our flux. So both of these, higher temperature and a higher concentration, both cause a higher diffusion or higher flux of atoms.